you to think about right now is, imagine you have, and it's kind of it's a little bit of a stretch right now, but imagine you have two magnets, right? And what happens is magnetism and electricity, they're very closely related. You can't have one without the other. All right, so that's why usually if you're talking electricity, magnetism is a good kind of cousin to it, a good analogy, because it's easy for you to think about and see a magnet compared to an electron or a proton. You know what I'm saying? So let's say we take two magnets and we stick them together, right? So we bring them close together, and they're the same poles, so two north poles. And we bring them closer and closer and closer and closer and closer together. What happens as we push them closer together? I'm sorry? Yeah, they repel, right? Or reject. That's one way. No one likes to be rejected, so we just say repelled. It's lay you down a little easier. All right, so they repel each other, right? So you get closer, 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 and they start to repel each other. What happens the closer we get? What happens to that force the closer they get? They get stronger, right? The closer we get, the stronger it gets, right? Now, what about if we have one that's a north pole and one that's a south pole? As they get closer, they do what? They attract, right? And what happens to the force as they get closer? It gets stronger, right? So it's like slow, and all of a sudden it goes like that, and they want to jump on top of each other, right? So electrons or positive and negative charges work the same way. Okay? So what I want you to do right now is we're going to watch this. It's a pretty quick video, but it's pretty easy to see. This is set up, this Rochester Institute of Technology. They made a bunch of these videos that if we wanted to, we could take these videos and put them in Logger Pro, and we could do calculations doing video analysis. But they've got one ball here. It's what's called a pith ball. Usually it's like very light styrofoam. Pith ball is just very light styrofoam, and they've painted a conductive paint on it. So it's like a metal paint so that it can take charges, right? So you can charge it very easily. So we've got a large one there. You're going to see a guy come in with another ball attached to a rod that is also charged, and he's going to bring it close to this one. All right, so what we want to do is a couple things we want to do. I want you to see, can you figure out, are they like charges or opposite charges? All right, is each ball like charge or opposite charge? And then see what happens as it gets closer and closer and closer. What happens to this ball? Okay? Or think about the way that it moves. Make sense? Okay? All right. All right, and this is in slow-mo, so it's kind of easy to see what's going on. So first thing, like or opposite charged? Raise your hand if you say opposite. Raise your hand if you say it's oppositely charged. Raise your hand if you say it's like charges. All right, so it's like charged because they likes repel.
Wait, what?
Likes repel. Opposites attract. Right. I think you just got mixed up with the words. Right. Right. So they are like charges because they repel. The next thing, we can watch it a couple more times. What happens when, as it gets closer and closer and closer, watch how the hanging ball moves. Okay, so what happened to the way the ball moved as the rod get closer and closer to it? Chris?
Moved away faster.
Yeah, moved away more, right? So you see, as he first starts to come in, the ball just moves like a little teensy bit, right? And then it gets a little closer, it moves more, and as it gets closer and closer, the ball moves in these larger segments. Did you see that? Did you notice that? Okay. So it's just like what we talked about with those magnets, where as they get closer, they either repel. The force of repulsion gets stronger or it gets weaker, depending on what we're doing. Okay? Good? Make sense? All right, awesome. Okay. So we can kind of see that the amount of charge they have matters and the distance apart from them matters. Right? Does that make sense? Right? So that brings us to this guy named Coulomb. And he did some work with charged objects. Thank you. Right? He did work with some charged objects, and he came up with his thing called Coulomb's law. Now, Coulomb's law deals with, again, charged particles and how much force is being applied between them. And he found out that it is equal to F K1 times K2 over R squared. Okay? Now, I understand you don't know a lot of these things. They're all Q's. All right? I understand you haven't seen these things before. That's fine. It'll make sense in a minute. Okay? So this K right here, this is just a constant, right? It's a physical constant. So every time you see the letter K, you're going to plug in the same exact number. Okay? And luckily for us, in this case, it's an easy number to remember. Okay? What happened was this guy Coulomb, he would do experiments, right? Bring charged particles near each other. And he would notice that if he knew the charges and the distance apart, he would get a number. And doing some other calculations, he could find out what F is, right? And he would always notice that the F in these two divided by R squared never added up, they were never equal. But every time he did it, the ratios were the same. All right, so maybe he noticed it was like a 2-to-1 ratio every single time he did it. So what he was able to do is he was able to figure out what that constant number was that would make both sides of these equations equal to each other. Okay? Follow me? All right. So, and there's a bunch of these that run around. There's K, there's capital G, which deals with gravity. There's a thing called sigma, so O, and there's a million of them. Really simply, K is just 9 times 10 to the 9th. So whenever you see K, you're going to plug in the number 9 times 10 to the 9th. Okay. Q is equal to the charge of the object. Right? And we use the unit, the Coulomb. Or it's just capital C.
What do you mean by like charge?
So how many electrons, how many positives or negatives you have.
Is it going to tell us that, or do we just have to like figure it out?
You'll either be told or you may have to calculate it, depending on what the question's asking. Yeah. Okay. So it's kind of like you have 45 meters per second. That's how fast you're going. This is just how much charge you have, kind of like mass, right? Okay. Because the electron has a certain amount of charge to it. Coulomb could be like how many of those you have. Okay. And then R is the distance between the objects. Okay, so however far apart those two things are, that is your R. Sometimes you'll see it as D instead of R. Okay. If you look at this, you see that it's squared and it's in the denominator. If we think about that, if they're large distances apart, we get a small force. That makes sense, right? So if we're 2 meters apart, really it's 2 squared, which means this whole number is going to be divided by 4. Right? So we're reducing the force. But the closer we get, so instead of like 2 meters apart, now we're 0.1 meters apart. When we square that, now we get 0.01. Now that 0.01, if we take this number divided by 0.01, have we just made that force a lot larger? Right? So that's what happens with this inverse square law, that as you get closer, it gets stronger. And we saw that in the video. Right? The closer it got, the farther it got away, because there was more and more and more and more force pushing on it. Okay? Follow me? Good? Okay. So that's what we've got here for Coulomb's law. And it's not too bad. It's pretty simple. And we're going to go through a couple of these and do it together.